Bonjour. Hi, my name is Denis Heinz. I am the president and CEO of the company H2I. It is a pleasure for me to facilitate an hydrospatial session of the GeoIgnite Online 2020. You may wonder, what is hydrospatial? In a nutshell, it is marine geospatial. Geo is often associated with the land side and the dry side of spatial data and information, where hydro is the marine and aquatic side or wet side of the spatial data and information. In this session, we will have two very interesting presentations on the science element of hydrospatial. First, Dr. Daniel Lebel, Director General, and Dr. Gwyn Lintern, Section Head of the Geological Survey of Canada, are going to make a presentation on the national scale GIS for assessment of hazards. It will be immediately followed by a presentation from Mr. Marc Leblanc, Director of the Canadian Hydrographic Service of Fisheries and Ocean Canada, and Dr. David McCormack, Executive Director of the Canadian Hazards Information Service of Natural Resources Canada. They will make a presentation on detecting and responding to great waves.
Good afternoon, everybody. I'm very pleased to be with you to attend this virtual GeoIgnite 2020 conference and to speak about the evaluation of coastal hazards on our coast. With some recent examples, Gwyn Lintern, my co-author, will be following me shortly after my introduction. I'm with the GSC, the Geological Survey of Canada. Our mission is to provide the geoscience knowledge to our people and to inform the stewardship of Canada's onshore and offshore land. That's a vast mandate. We're doing this to inform the responsible resource development of our mineral and energy resource, but also groundwater, and also to keep Canada safe from natural hazards, which you will see are important. The GSC conduct this work through a systems approach. We collect data in the field or using instruments such as drones or satellites or geophysical instrument. We use this data to understand the process and develop through research and models that will allow us to make some understanding and prediction about how the Earth works, how Canada's various processes such as landslide operate. You see on the screen there massive rock slides that are occurring on the northwest coast of Canada on the Beaufort Sea, and there are features that are receding very quickly. We have also a process like that that are occurring in the submarine area. So we need to develop some system to monitor these features because they can be putting some infrastructure and communities at risk. You'll see some example of this through this session. We have a general strategic area called Geoscience to Keep Canada Safe, where we have programs that touch on climate change impact and adaptation, as well as our public safety geoscience that focuses on geohazards. We have a number of thematic area that looks at natural hazards and try to assess risk to infrastructure and communities and work with stakeholders nationally. The examples that we have here are more specifically touching on slope stability in the submarine area, but also on land. Here's a picture of our overall situation for submarine landslide. That's out of a recent publication by a series of authors from the GSC, but also with others. We have a number of submarine landslide recognized on the west coast, which is an active plate boundary, as well as on the east coast, where we have a lot of sediment on the continental shelf, but also in the St. Lawrence River. So you'll see some example of these features that can be initiated by a major earthquake. So you see a map of our work on earthquake on the right there that informs the building code of Canada to keep our infrastructure solid. So on this, I will turn it over to Gwyn, who will carry on from this point to present you with some specific example of our work.
Thanks, Danielle. As a geological survey, we spend a lot of time using geospatial data, both on the survey and mapping sides. Some examples I have to show today are just very recent examples that we've done in collaboration with the Canadian Hydrographic Service and the Canadian Hazards Information Service. So just a few examples of work we've done together with these two other agencies I'm speaking with today. The first here is in Boundary Bay in the south coast of British Columbia. The project, I'll just close the project is to understand the effects of multiple hazards on these communities, and particularly the community of the Semiahmoo First Nation here. And one of those hazards is storm surge. You can see storm damaging the White Rock Pier here, and the First Nations community trying to mitigate against storm surge overtopping their main road to their community. So storm surge is an issue here. And also an issue is the threat of tsunami. And here we have a simulation of a tsunami, 9.0 magnitude tsunami being generated, propagating through the Strait of Georgia and up into Boundary Bay. You'll see in a moment. These northern kind of bays seem to capture the tsunami all too well, including Boundary Bay. And we have also in this area, there's an island here with steep cliffs. We've recently found a fault off of that island. And so the fault, along with indication of previous landslides, gives us a kind of a third hazard to identify here for a potential tsunami into Boundary Bay. And of course, there's climate change in this area. The sea level is expected to rise about 0.5 meters in the next 100 years. So in order to model all of these hazards on the community, we've put together a very large digital elevation model. And these are all of the communities, they're all of the agencies it involved to put together a complete digital elevation model. I'm sure some of you in this audience will appreciate how hard it is sometimes to get LiDAR and multi-beam data. And here we have just how many people we need to get in the same room with all their datums to produce this digital elevation model of the area. And but you can see the result is quite stunning. And we have the offshore data here in blue showing tidal channels, and the onshore areas here in green and brown, and showing quite clearly the very low-lying areas that are at risk of these sea level kind of inundations. Just very briefly, this is a different project, but in the same area. These again are the low-lying areas that that are at risk and that have these storm surge issues each year. The idea is to, rather than continue to keep building dikes out of concrete and stone, is to build up the seabed with sediment and a new salt marsh. So plant, and this will be done in some small areas here, to determine, as has been determined with mangroves and other types of salt marshes around the world, if salt marshes could instead be used for wave energy dissipation. And our job here will be to understand how well this is working by using lots of survey data, geospatial data, including we hope to use CHS's small catamaran that collects multi-beam data. We already have their LiDAR bathymetry collected from an aircraft. And we have ourselves been starting to use drones to do coastal surveys. And here's an example of a coastal survey of the eroding cliffs in the Arctic Ocean near Tuktoyaktuk. And so we hope to use this to determine changes and how well these living dikes are working in the low-lying Boundary Bay area. Now we move up the coast to Douglas Channel. This is an area that's been in, I guess, in the news a lot lately for having a lot of projects being proposed in this area. Douglas Channel and Kitimat Arm. Kitimat Arm is right at the end of Douglas Channel here. And here's a list of the projects that have been proposed. Half of these, I guess, at least half of them are going ahead. Others have been canceled. But still, there are billions of dollars worth of projects going ahead in Kitimat Arm. But Kitimat Arm has kind of a history of tsunamis that we know were caused by submarine landslides. The proponents know it, we know it, and the licensing agencies and the authoritative agencies also know this. So it's not a shock here. But we went in to do more detailed work on the frequency and magnitude of these type of events. And this beautiful multi-beam data collected by the Canadian Hydrographic Service shows well the events that caused tsunamis in 1975. This landslide here caused an 8-meter tsunami in 1974. This one running down here caused a 6.3-meter tsunami. And we saw other excavations too that I'm calling this pre-1975 for now, but we actually have better dates on that. We do three-dimensional surveys as well. This is a profile through the delta front. In a sense, it's four-dimensional because it shows this current pile of rubble from the recent slide as well as previous slides going back in time. And so we can start to count the frequency and magnitude of slides, and with the beautiful multi-beam data we have, we can also see which ones overlap which and kind of generate a story of the evolution and frequency and magnitudes in the area. Sort of at the same time that these projects were well, separately, an assessment was done of the whole BC coast of all of our multi-beam looking for submarine landslides. And this one was found further down the channel from Kitimat in Douglas Channel. There were actually two, one here and one further off the screen. And these are 1 kilometer long blocks of rock falling off the fjord walls. And when we went in with the ship, sure enough, we saw that on the above the ocean as well, we could see indications that the sort of slope here had failed. And again, we use geospatial data. Again, we're putting together multi-beam with LiDAR. This is the coastline here on this image, and we're monitoring these unstable, well, what we thought were unstable slopes with different types of instruments. Here we have corner reflectors that we've put in the mountain sides to use INSAR repeat mapping. And so far, the changes we see are very small to nothing. I mean, these are kind of within the range of error for the instruments, and again, also for these pressure sensors underwater. So, and the geological evidence we collected here also indicates that these slides are no longer moving, that they were something that took place up until 8,000 years ago and are moving now. But while we were in there, we took the opportunity to do sort of coast-wide assessments, and here's an image of a terrestrial surficial geology map. We did 5 of these map series while in this area, official GSC maps, and landslide susceptibility modeling using various parameters plugged into the GIS to output kind of, areas that we would expect to see landslides. And here's another example of a regional map that we did while there, of the seabed, of the geohazards, of what's below the seabed and what's on the seabed. These are all official GSC map releases and are available here at GeoScan. So not only the maps and the images and the documents we produced, but the layer files themselves are available there. And the last slide is this one here, showing we do national scale assessments, and this is just one of our recently released publications on national scale assessments of submarine landslides. Here what I wanted to show was these kind of light green streaks, green bluey kind of streaks are where we have multi-beam. And all the sort of more blue colors are where we don't have multi-beam. And where we find faults and submarine landslides are basically where we have multi-beam. So clearly we have to go out and collect more multi-beam to understand these hazards better. We have a new project called Marine Geoscience for Marine Spatial Planning, and that's really aimed at getting in before proponents propose these large coastal projects with a series of maps that indicate the geoscience of the areas. And that's the purpose of the new program. We're working very closely with CHS on that, using the kind of traditional ship-based multi-beam collection methods, but we also collecting data from using our new tools, such as these AUVs, underwater multi-beam AUVs, and other methods. And that's pretty much a snapshot of some of the things we do. If you have questions, Danielle and I are here. Thank you.
Good morning, good afternoon, wherever and whenever you are, and welcome to a joint presentation by NRCan and the Canadian Hydrographic Service of DFO on the work that we're doing at the moment and that we plan to do over the next couple of years with respect to tsunami monitoring and alerting for Canada. My name is David McCormack, and I'm joined by my colleague from CHS, Marc LeBlanc, and we'll be delivering this presentation jointly, going backwards and forwards throughout the talk.
Yeah, good morning, everybody. As David said, my name is Marc LeBlanc, Director of the Canadian Hydrographic Service Office in the Pacific region, and it's great to have an opportunity to speak with you about some of the work we do with Natural Resources Canada on the coast with respect to tsunami monitoring and coastal hazards.
So we'll start off, we assume that most of you are probably familiar with what a tsunami is in general terms. Tsunami is generated when there's a displacement of the ocean floor. The water column above it is then displaced equivalently, and that generates a wave which moves away from the source. And as the wave moves into progressively shallower and shallower water, it can become larger and larger to the point where it can cause a significant damage to structures, infrastructure, and so on that's built near the coastline. Usually these displacements we associate with movements of the seafloor as a result of displacement along a fault in an earthquake. Tsunamis can also be generated by landslides, volcanic collapses, and other types of events that disturb the seafloor or disturb the water column. Most of what we're going to talk about today is focused very much on tsunamis that are generated by earthquakes, and in particular, tsunamis generated by earthquakes, which may have an impact on the coastlines of Canada. The current situation in Canada with respect to tsunami monitoring and alerting is as follows. The primary method by which potentially tsunami-causing earthquakes are generated is notifications that come from the real-time data collected through NRCan's Canadian National Seismographic Network. It's a network of about 200 sensors distributed across the country, which are constantly monitoring for the occurrence of earthquakes in Canada or near the Canadian territory. That data is sent in real time to the National Tsunami Warning Center, which is located in Palmer, Alaska, and is operated by the National Oceanic and Atmospheric Administration, NOAA. That data is supplemented by real-time tide gauge data that comes from the Canadian Hydrographic Services network of tide gauges around Canada's coastlines. And these two data sources are integrated together with data from other jurisdictions, data from buoys that operate out in the deep ocean, and satellite data to provide the scientists at the Tsunami Warning Center of an overall picture of events which may generate tsunamis. If an event occurs that has the potential to generate a tsunami that may affect the North American coastline, alerts are issued. Those alerts are passed from Palmer to the Canadian federal government for dissemination, to provincial levels of government, and also to the Coast Guard for dissemination to ships at sea. So that's the current picture, and we'll talk a little bit in more detail about the sensor networks and the activities to support those next. The map that you see is a map showing the distribution of the seismic sensors that contribute to the tsunami monitoring network. You can see dense clusters of the seismic sensors in parts of the country where there's high seismicity, lots of people and lots of infrastructure, for example, Vancouver Island or the St. Lawrence Valley, and fewer sensors in areas where the seismicity is low, such as the prairie regions, or where there are much reduced amounts of infrastructure and population, such as the high Arctic.
So now I wanted to look at the Canadian Hydrographic Services network of permanent water level gauges. So these gauges relay real-time data to a central location here in Sydney, British Columbia for the Pacific coast, and we have similar locations in the Atlantic region. The gauges have a variety of relay methods, including satellite, cellular, and landline communications, depending on the location and the requirement to have redundancy in getting that signal ashore. The data is sent to a central monitoring service and is disseminated directly on the internet to the public, as well as to our staff who are constantly monitoring the network for the possibility of a tsunami event. Within these gauges, we have the ability to monitor multiple stations at a time, as you can see from the image on the display. Station data is transmitted via internet protocol and separate satellite via the GOES, or the Geostational Operational Environmental Satellite System, operated by NOAA. During the tsunami response, CHS is responsible for monitoring the Canadian water level stations along the BC coast for the event. Staff are in constant communication with other government organizations and agencies who are in turn responsible, as David said, for sending out those messages. CHS has also created software that allows response staff to carry out this monitoring function from a laptop anywhere there is an internet connection. The software is actually on a USB stick, so it's portable. So if it's not possible to monitor in one location, we can monitor in another. You can see here a good example of what the actual data from a warning from a water level gauge looks like. So these are the actual readings that were received after the major seismic event in Haida Gwaii that occurred 28 October 2012. You can see clearly from the various gauges where an actual tsunami wave was recorded. And you can look at the image to the right, you can actually see there's kelp in the trees, which is clear evidence that there was a tsunami event on the west coast of Hawaii. Fortunately, the area is sparsely populated. There was actually no settlements or towns on the west coast. So it was only after an investigation of the seismic event that there was a clear indication of where the wave occurred. And put that together with the actual recordings from the gauges, you get a good picture that a tsunami event happened on the coast of Canada. For future enhancements, we're really looking at the co-location of global navigation satellite system receivers with our tide gauges, which provides a great enhancement for us. And I'll turn it off to David to tell you a little bit more about that.
Thank you, Mark. Yeah, so we're interested in constantly improving both the quality and accuracy of the monitoring and alerting, and also ensuring that the alerts, when they are generated, are disseminated as efficiently and widely as possible, so that infrastructure and the public can react accordingly when there is a hazardous event that they need to respond to. So in order to support that, we've been working actively together to look at new technologies as they become available that will help us complement what we're currently doing. If I can have the next slide, please. This is one example. This is a location where we've installed one of NRCan's GNSS receivers close to an existing CHS tide gauge. This is at Bamfield on the west coast of Vancouver Island. And the purpose of this is several-fold. First of all, it aids with the calibration of the tide gauge and its continuous operation, and also after an earthquake, when there may be significant displacement of the entire area as Vancouver Island moves up or down during and after a large event. It helps to provide real-time re-evaluation of the datum, so that the tide gauge data that's coming out can continue to be used directly in order to provide information about any potential tsunami. Go to the next slide, please. Then you can see our current network of real-time GNSS receivers in this part of the country. You can see strong concentration in the areas we expect to be deformed significantly by large earthquakes, in Vancouver Island and Hawaii in particular. And we're working right now with our colleagues in the National Tsunami Warning Center to stream this data appropriately processed in real time to Palmer, Alaska, so that that can be used to supplement and complement the data that comes from the seismic networks. And that's very important in helping us to rapidly determine whether the type of earthquake that's occurred is one that's likely to have had mostly horizontal movement, which case is not such a risk from tsunami, or has had significant vertical movement, in which case the risk of a tsunami is correspondingly much greater. And that's work that's really come out of lessons that we've learned, for example, with the 2012 Hawaii earthquake, as Mark previously demonstrated. Next slide. Another area of our focus is to ensure that the alerts are properly disseminated. Within Canada now, we do have a formal national public alerting system, which is coordinated through Public Safety Canada, a number of other federal government agencies, provinces and territories, and some private sector partners. This system allows the dissemination of time-sensitive alerting information for public safety. You may have seen it used already, for example, for amber alerts or for severe weather warnings in your part of Canada. We're working at the moment to develop an earthquake early warning system that would use this dissemination system. And the intention will be that we will also be able to inject tsunami warnings into the system, so that they can be broadcast on televisions, and also issue an alert which you will will trigger your cell phone. This is a system that's will progressively be used more and more widely for a number of other hazards within Canada, and represents an efficient and effective way of ensuring that the the public, media, and others receive immediate timely notification when there is a hazard in their area they need to respond to.
Now we'll look at some of the collaborative initiatives that we have with Natural Resources Canada. And one of the major ongoing projects that we do is mapping the ocean floor, in particular the areas where you have an ocean fault. So as you can see here, with the Haida-Gwaii offshore fault, the collection of high-resolution multi-beam bathymetry greatly assists in actually determining what that fault looks like and actually where the fault actually bends. And this data was used to help determine that there was a possibility that you could have a thrust earthquake event in the area. So you can see there's a good correlation between the location of the fault and where the actual tsunami event occurred. And then the collection of that water level data contributes to the production of a model of the actual tsunami event. So you can see here where the red is where the amplitude of the wave was higher, and you can actually see how the wave spreads out throughout the Pacific Ocean. And this wave was actually recorded in Hawaii as well. There was a 0.8 meter wave as a result of the seismic event in Haida-Gwaii in 2012. The same for other earthquakes that happen throughout the Pacific Ocean. The gauges Canadian Hydrographic Service can actually pick up and record that wave several hours after the actual seismic event. And that helps with the overall modeling of tsunamis in the world's oceans. One of the other coordinated missions that we do is the connection of LiDAR data. So in this case, this was a project where bathymetric LiDAR was collected in Boundary Bay on the west coast of Canada. And this data is very important for the production of inundation mapping models, determining sea level rise, production of digital elevation models, and the ability to accurately depict the ocean and shoreline mapping. So this improves products that the Canadian Hydrographic Service provides to the public, and it's also a great opportunity for other organizations to use that data to improve the actual coastline and what it looks like. And you can see here there's an excellent correlation of the LiDAR data with the existing products that we have. So those type of projects will continue, and it shows the good work that comes out of the cooperation between CHS and NRCan. So I'd like to thank everybody for participating in the event today, and we're now very happy to take any questions that you may have on our presentation. Thank you.
Wonderful. Thank you very, very much. And we do have all of our speakers joining us for the Q&A. I'll just make sure that everyone is, if you are muted, if you could unmute yourself, please. And I will pass it over to Denis Ains, who will conduct our Q&A.
Thank you very much, Tessa. It was a very interesting presentation that we just got from Danielle, Gwyn, and David and Mark. So we did receive some question online as the presentation was made. So I will start with those one. I have here Sam Jardine was asking, is NRCan planning on expanding their own in-house drone imaging capabilities rather than relying primarily on other organizations? So I don't know, want to chip in this one, possibly Danielle or Gwyn?
I can speak a little bit about that. We've got quite a few. David has got some for some of his service. In the GSC, we do use it to do some research on understanding coastal process that are airborne, but we also have also some submarine AUVs that we've been using to survey the seafloor, in particular for the limit of our continental shelf and a few other purposes.
David, do you have anything to add from your service perspective?
No, it's a work in progress, of course, as the technology evolves, and in particular for these types of applications, as the endurance of systems evolve. It's something we continue to invest in and follow along with.
Okay, thank you, David. So we have a second question here coming from Marco van der Kuij. Have you considered using satellite imagery, archives, and SAR imagery to map the coastline, including tidal mapping, in areas that have not been mapped, as well as Boundary Bay? Maybe CHS can answer on that, Mark?
Yeah, we've certainly been using LiDAR data, bathymetric LiDAR, quite a bit now, and for that nearshore area, and really using to learn how to process that type of data effectively and integrate it with the rest of our data system. And it's a cooperative ability we have to work with NRCan that's really helpful in getting a good overall picture and elevation models created from that. Satellite imagery from archives is good more to look at changes over time. And we have as well within CHS on the East Coast have used satellite bathymetry for some specific areas, and we've incorporated into products. And it's used annually on areas such as the Mackenzie River, where there's a big change in how the river flows on an annual basis that we need to look at before any navigation products can come out. So certainly the Boundary Bay using aircraft LiDAR was a start, but we're looking at all those new technologies now and other technologies that we can use, always looking at imagery archives for change detection with respect to that. In particular, it helps in terms of shoreline erosion and things like that. So a lot of possibilities there and a lot of different tools available depending on what the end result is that you want to have.
Thank you very much, Mark. Anyone else want to answer about satellite imagery, archives, and SAR imagery?
I think if I can say, another question came. We're using INSAR to monitor landslides or crustal movements. So in addition to the GPS station that David McCormick talked about, we're using INSAR satellites to monitor specific landslides, and we're using we're using reflectors and we're just doing it on sort of points of land. We haven't done it for the whole coast like this question asks. We've done it just in specific targeted areas so far, and we haven't done it to determine tidal mapping. It's a good suggestion, though. For those areas we don't have tide stations, it's a good suggestion.
Thank you very much, Gwen. There were additional questions that were asked, as Gwen just mentioned, during the presentation, which are related to satellite imagery as well. And I think we have covered them quite well with those responses. Possibly one which is more specific for whoever thinks can chip in. What source from Ramin Azar, what source of satellite data is used to track and forecast Pacific Ocean waves? Is Sentinel-3 Sentinel-3 provides sea surface temperature? Has it been utilized for this purpose? Yes, David? David, you're on mute.
Yes, I'll have a go at that just to follow up on what I wrote. Actually, a lot of techniques have been explored to try to use various types of satellite data for operational tsunami detection, recognizing that just because a big earthquake occurs, it doesn't mean that a tsunami has been generated, and that it's very would be very useful if we could detect those tsunamis right out in the deep ocean before they start to impact shorelines. That's done at the moment primarily using buoys, but of course the density of buoys is limited by their cost and the cost of servicing them. So satellites have been tried. They're direct measurements of the sea surface is one way of doing it. And that's been demonstrated a couple of times, most particularly with the 2004 Indian Ocean tsunami. But one very interesting technique that's being used is to actually look at the ionosphere, which gets distorted by these tsunami waves as they move by in a coherent manner. And those ionospheric distortions actually get reflected in distortions to our GPS signals from GPS and other GNSS satellites. So by looking at the constellation of satellites and looking at all the signals together, scientists have been able to extract the signals from those tsunamis as a generator. And that's something I think that is actively being followed, with the idea of perhaps being able to operationalize that in the future, since we do have quite a density now of GNSS satellites in orbit. So you could almost have global continuous coverage of the oceans to be able to detect those large waves right out at sea. Thanks.
Thank you very much, David. There is a question here from Sven Cohen. Does NRCan and CHS have plans for coastal mapping in the Arctic? If so, what technologies would be used for this? Maybe Danielle and Mark on this one? Danielle?
I'll address broadly. We got some planning underway for a Canadian coastal and ocean mapping strategy that would attempt to focus efforts to areas of highest need in terms of understanding process that might have benefits in terms of understanding risk to infrastructure, for instance, or managing our offshore or on the coast. There's always a challenge between the offshore and the onshore and what technology you use. So it's important to do good planning and partnership on this, in particular with the private sector, which have emerging solution, as you were mentioning, Denis, in terms of LiDAR in the near shore. So as technology evolves, we'll be able to cover more ground. We have the longest coastline in the world, so it's an enormous challenge, and we have over 7 million square kilometer of offshore territory. So to actually prioritize where we're going to go is quite important. So I encourage you to check out the report that's coming up with the Ocean Research Canadian Alliance, following a workshop that was held earlier this year. That will give you some details as to where we hope to go. And that's a partnership with the Canadian Hydrographic Service.
Thank you very much, Danielle. Mark, anything to add, or it covers quite well the plans of CHS as well?
Yeah, it does. But I can say, Denny, that since we've started to put a concentrated effort in the Arctic through the Oceans Protection Plan, satellite imagery is absolutely critical to updating the products that we have in there, because we're looking at charts that would have created, up to 30 years ago or more. So the coastline, the ability to have satellite imagery to update that coastline, to define what the high and low water lines are in those areas, is dramatically improving the products that we have there. And the key is then that extraction of the coastline from the imagery is available to other government organizations. If we look at an area that we need a larger scale product, we found that LiDAR, even taken directly from the survey vessel looking to shore, gives us a very much more detailed coastline than we ever imagined. And we're certainly looking in the shallower areas of the Arctic to employ bathymetric LiDAR there. The advantage is, be it good or bad now, is that often conditions are such that we don't have any ice beached up on the shoreline now, and we can get a good picture of it with bathymetric or satellite imagery. So it's dramatically going to help us in the Arctic, and it's putting all that information together. We're still, the key focus is multi-beam and the key shipping routes, but when you're updating a product, the coastline has to match with the bathymetry in a spatial situation. So we have to make sure that we have a key anchor, and that's the coastline in our products to do that. So very good points, and it shows that working with other departments is very important for us to keep that work going and to progress our mapping and understanding of the Arctic.
Thank you very much, Mark, Danielle, David, and Gwen for this very interesting session on hydrospatial. As I mentioned in the introduction, in a nutshell, being marine geospatial. And that's all the time we have this afternoon. I invite all participants that would have additional questions to be in touch directly to our speakers, and I'm sure they will be happy to answer to you. Thank you, and have a good end of day on Geo Ignite 2020.
Thank you very much, everybody. Thank you to our speakers. Please feel free to attend our panel, which will be in the next room, as well as our Maxar happy hour that will occur at 6 p.m. Eastern time this evening. All of that information and the way to access it is the exact same as we have been doing throughout the day, throughout our schedule. And as Denis has mentioned, if you have any additional questions, please reach out directly as well as through our Slack channel. It is a great way to get into communications and continue this conversation, as it is very much an interesting topic. Thank you very much, and we will see you all soon.
Thank you.